How many of you guys here actually know what a babblefish is? Okay. Just one? Okay. I need to update the cover page for this to be more like Gen Z relatable, I think. Anyway, well, we'll start with some logistics, and I think you're already familiar with this information. The only thing is that this Friday, we don't have any tutorial, so focus on completing your assignment. There's going to be another A1 tutorial next week. It'll be more of office hours in person with the TAs. So you can, and yeah, that won't be recorded for privacy, obviously. But yeah, there's no tutorials this Friday, okay? And another thing that's very important is, it's been already mentioned that please don't be this person when you're not even done with your assignment, you're done with the project. Please don't upload your course assignments on GitHub or some public repositories. It goes without saying that it violates copyright contracts, and also the fact that it's kind of a little bit selfish if you think about it, because you're taking away from the learning opportunity of future students. So please don't do it. Okay, yeah, please share your feedbacks with the lecturer as usual, and this is going to be the high-level plan for the next couple of or 3 lectures. So today we'll be starting off with statistical machine translation and some historical background. We'll be looking at noisy channel model and alignment-based models, which to focus a lot more on the statistical part in previous years, but obviously we have sort of slowly moved towards more neural machine translation, which is going to be the meat of the lecture. And you'll be doing your assignment too, which is also on machine translation using neural methods. Okay, so no lecture on machine translation is complete without a cursory stop, historical stop on the Rosetta Stone. The Rosetta is an Italian name of the Egyptian town called Rashid, where the stone was first discovered in the late BCE, and then they were rediscovered by the French soldiers during the French Revolutionary Wars when Napoleon invaded Egypt, and then it was acquired by the Brits in the 1799. But the idea is that the stone is very fascinating because on that stone there is a transcription of the same decree, Macedonian decree that was decreed by Alexander's troops or the Macedonians when they conquered ancient Egypt, and it had 3 different texts of the same decree. And by 1800s, the ancient Egyptian hieroglyphs and the ancient Demotic, 2 of those 2 languages were lost in the ravages of time. No one knew what they meant. Only the last one, the ancient Greek, was understood. So this allowed, in the early 19th century, a lot of researchers worked on the stone. We're going to use this guy, John Champollion, as a composite character, as a composite researcher, and to decipher the stone, the other two languages. And what he noticed was that certain symbols appeared in roughly the same positions in Egyptian cartouches. So Egyptian cartouches are basically royal names. They usually have an oval shape, and they contain the name of some royal person. They could be in tombs or obelisks or anything that has royal attachment from the Egyptian time. And he noticed that this Egyptian symbols, and at that time it was common knowledge about some of the Egyptian rulers like Ptolemy and Alexander or Cleopatra. So he noticed that certain symbols appeared roughly in the same positions for Ptolemy and let's say some other, like from the cartouche of Cleopatra. And also the fact that these cartouches had symbols associated with them in a way that it's partially phonographic, meaning that the pronunciation, the enunciation had some sound attached to it, like a sound component to it. So using that, basically the idea was that you can juxtapose 2 cartouches of known words, Ptolemy and Cleopatra, and if you roughly know the sound of both the names, Ptolemy and Cleopatra, you can sort of find a correspondence. And that's exactly what he did. He lined them up, and he basically saw that the P in Ptolemy and then Cleopatra, this could be PP, so this rectangular symbol could correspond to the P sound. And similarly, like this lion or animal symbol could be L. And by that way, like he also looked at other cartouches which are available from different artifacts, like obelisks of Alexander the Great, and then he deciphered the sounds. And basically that was the underlying idea. And the reason that's so important is because this is the intuition, or this is the historical motivation of how we do any translation. So modern day translations are based on the fact that we use parallel text in order to do the translation, okay? And language, any language by itself doesn't really mean anything. Language's meaning is grounded in some other object or something. Like language by itself doesn't mean anything. So we'll look at, so this is the historical background. So now let's define the problem that we're going to be talking about. The problem of machine translation is essentially, translating, you're given a source language and you're trying to translate it into some target language. So for our lecture, our source language will be French, Canadian French, and the target language will be English. So at a high level, we can delineate the different levels, classes of methodologies of machine translation into 4 different ways. One is like, as it's displayed by this so-called vacuous triangle. First, you can have just direct translation from words to words, and then you can move up the chain. You can do like syntactic transfer, you can do semantic transfer. But modern day, like ideally what we want to do is we want to absorb the meaning of a source sentence into some abstract form, and then basically generate another sentence in another word, the target language, from that abstract meaning. And if you think about the modern ways, that's kind of what we do. So in an encoder-decoder kind of model, we first encode the source language into some abstract Latin space representation, and use that latent representation to again generate our target tokens in the target language. But let's go from the bottom. Let's look at what's the problem with doing direct translation, or like how did it evolve to where we are today. So the first is direct translation. So direct translation is the same thing as having a dictionary, right? So you can go by using a bilingual dictionary that aligns words across languages. That can be helpful, but it's for only simple cases. So you can really have you can be very fluent just by using a dictionary to translate something very fluently into another language. And why doesn't direct translation really work? Because of differences across different languages. Let's take a look at some of those intrinsic linguistic differences that makes direct translation difficult. I think Gerald alluded to some of them in the introductory lecture, but let's sort of formally go through them. So first of all, there's different morphologies, meaning that it's like different. So a morpheme is the primitive component of a word, and different morphology means that they have different mapping between languages. So for example, one example could be like polysynthetic versus isolating morphemes per word. What that means is that in certain languages like Yupik, a single word could basically mean a sentence, okay? You can say a whole sentence using just a single word. Well, isolating morphemes like languages in Cantonese where words are basically indivisible, like each morpheme conveys one meaning. So similarly, if you consider the suffixes and prefixes in different languages, they can be very different in terms of conveying their meaning. So agglutinative, meaning adhesive, like languages like Turkish, where you can have certain prefixes and suffixes attached to a word to convey a certain meaning. Whereas in fusion languages like Russian, you can have one affix, or you can have some affix that means a lot of 3 different things into one affix. So this kind of morphological differences or structural difference of typology makes it really difficult to do a direct-to-direct translation. Another issue is with the syntactical structure. So you have, in English, we see subject, verb, object is the common sort of flow of a word. But that is not true for different languages, right? So for, in this slide, you see some example where, Japanese example where the flow is subject, object, verb, and in Arabic, it's verb, subject, object. So we'll see this kind of problems when we look at alignments. Why do they matter? Because of this different flow, you can just take one language and a source and target language and basically map them sequentially because the flow can be different. Another problem is also like, the distance between, let's say, verb and satellite verbs. So for example, the bottle floated out could be reversed in order, like in some other languages. So it sailed out versus, yeah, so this could be different. And there are many other examples, but essentially this is a gist of some examples which elucidates the problems. So the next problem is ambiguity across different languages. So the lexical ambiguity is meaning that, the specific meaning among many-to-many word mappings are possible. So as an example, think of the meaning of the word paw in English can be translated into French as pâté, which means foot sometimes, or which can also mean pied. But foot or pied, neither of foot or pied actually means paw. Paw is something that, animals have paws. We don't say that like four-legged animals have paws. So if you do a mapping from English to French and then French to English, the meaning can completely change. Another example of a common example is like, same token sequence but different inference. So Rick hit the Morty with the stick. Rick hit Morty with the stick. So I think a better example here is a man saw a policeman with a binocular, right? So I think that's a better example. So the policeman with the binocular, or you're watching the policeman with a binocular. So those kind of ambiguities, right? And then semantic differences. So same structure but different meanings. So I'll pick you up can be literally I'll lift you up, or it could be that I'm giving you a ride. So I'll pick you up from a certain station or location, or it could mean something different in a, let's say, a club situation. So and then again, there's also pragmatic differences. So pragmatic differences is something, I think the example that was given or that's most used is that if I ask you what is the time, and if you say, no, do you have the time? And if you reply that, yes, I do, that's not an appropriate answer. So that's an example of a pragmatic difference. So, and I think the textbook reading actually goes in depth very, with detailed examples of all kinds of different problems or difficulties. You can read it if you're interested, but at a high level, like these are some of the challenges that makes the direct translation really hard. So as in a historical note, like because of this difficulties, machine translation was a hard problem for a very long time. Despite sinking in a lot of money into this research problem, there was no headway until there was a change in perspective. And that's where the information theoretic like Claude Shannon's, it's attributed mostly to Claude Shannon, but Warren Weaver also had similar research during the same time. So without the success attribution, the main idea is that we have to look at machine translation through the noisy channel, or the noisy channel idea from a, or from a signal processing sort of concept. So the idea is that when we speak in a language, or when we look at some other foreign language, we're actually looking at the source languages, but in a distorted form, meaning that if I hear someone speaking to me French, or if I see a French sentence, it's actually English, but it's distorted through going through some channel, okay? And at the bottom is sort of high-level formalization of the noisy channel. So it's from a signal processing perspective that you have a transmitter that's transmitting a source language, and that's going through a noisy channel, and on the receiver side, you're observing the distorted foreign language. And how can we use this for our purpose? So this noisy channel, when I first saw it, it was a little bit confusing because we're really interested in, if English is our target language, we're really looking for this guy here. So we're given some French and we just want to get English, okay? But we need to, in order to follow the noisy channel, we need to use the Bayes formula. We can reformalize this argument, argmax of probability of E given F into probability of F given E times probability of E over probability of F. The denominator probability of F doesn't change the argmax argument, so we'll drop it from our discussion in subsequent slides, okay? So we have to formalize this as E star is probability of F given E times probability of E. Now here we are at how the noisy channel formulation. So I think it may be very, very obvious to some or most people, but essentially, what can be confusing is that we're doing sort of a reverse way. So remember that here our observations are F, right? We're given French, and what we want to get is target, which is English. Okay, so instead of doing, by doing this Bayesian formulation, what we essentially did was that we introduced a decoder in the process. So observed F, or the noisy version, will go through a decoder. We need a decoder to decode it into our target language. And in order to have a decoder, we need these two models: the language model, the target language model, the language model of English, and a translation model, PF given E. So the translation model does what? You give it some English sentence or English sentence. It generates the corresponding French sentences for you. So that's the translation model. Okay. So yeah, so this is the formulation. So the language modeling part in this lecture. So the language modeling part, if you think about it, you've already seen this. We know how to model language. We know the n-gram models, we know bigrams, we've seen trigram models. We have also seen RNN, how we can do language models. So this part we already know. So what we're going to focus on is how can we get like a translation model, okay, probability of F given E. And once we have that, we also have this piece that how do we decode. So in today's lecture, we're not going to look at like decoding. We'll look at decoding into in next lecture when we look into like beam search and like decoding methodologies. But today's lecture, we're more focusing on the intricacies of this translation model. So any questions about the noisy channel formulation? Okay, good. So yeah, so in this formulation, now that we've formulated in the noisy channel perspective, so our P is the language model, and which basically encodes the knowledge of English word order. We'll see why that is important. And then probability of F given E is a word or phrase level translation model that encodes knowledge only on a unordered basis. So essentially it gives us the French generation given some English words or sentences. So combining these two models, we can have naturalness and fidelity. So now the question is, you can say that why do we need the language model here? Yeah, so why do we need this guy? Why don't we just go with the translation model and maybe use that? So this can be exemplified in a simple example. So if you just go through the translation model, here we use Spanish as our target model, as our, as what we observe as the foreign language. So if we use just the translation model, then for something like using just this, it will show that the best possible English sentence translation is have I that hunger is the best translation using only the translation model. But knowing English, we know that this is not right. This does not syntactically or semantically sound right. I'm so hungry is a better choice. So when we multiply this with our probability of English or our language model of English, it corrects it to the right or the most fluent translation, which is I am so hungry. Well, I guess it's, yeah, intuitively think of it as, how many of you know what the base rate fallacy is? Okay, so the idea is that if I told any of you that, oh, the probability of you dying from Ebola is 99%, right? But that wouldn't really scare you, right? Because you know that, well, yeah, sure, but the probability of you actually catching Ebola is like 0.001% being in Toronto and in this lecture hall. So it doesn't matter whatever the probability of you dying from Ebola is. So essentially when, sort of you can think of it as the same way that the language model is giving it the naturalness and the fidelity, right? So using just the translation model gives you a partial picture, and when you also need to include the other part of the information, which is that what is the language order like. That gives you a fluent translation. Okay, so as I mentioned that today, so we're focusing on the translation model. So how do we learn a translation model like probability of F given E? So the solution is drawing inspiration from the beginning of the lecture that we need some, if we have some parallel text, then we can just use them to learn this translation model. And we do have a large collection of very accurate parallel text. Historically it's been through government documents of countries that have multiple languages as the official state language, like Canada, where every parliamentary debate or any official government proceeding is recorded both in English and equivalent French. So the Canadian Hansards are bilingual parliamentary proceedings that were kept and long been used as a key data corpus for French to English translation, or as a translation corpus, as a very, very important translation corpus. And different languages have different, availability of amount of parallel corpus. This is just showing until 2010, because from 2010 to 2024, if we included that figure, it would be really hard to see the relative growth of popularity, because it's been such an exponential growth over the last 5 or 10 years. So, so in order to, even if we're given this like text or parallel corpus, so first thing is that we can't take alignment for granted. So the de facto first step for any translation task or getting the translation model is to have an alignment between this parallel corpus of text given. And this parallel corpus can be aligned at different granularities. By that I mean that it can be granular, it can be aligned at a document level, it can be aligned at a paragraph level, sentence level, phrase level, and so on. Before the advent of neural machine translation, statistical machine translation relied heavily on explicit alignment between bytext. And for the subsequent conversation, it's very important to understand this bottom equation over here. Basically, this is how in order to do the alignment, we introduce an alignment model or a variable, alignment variable A, and we sum it out. So we can do this, right? So the alignment index pairs is basically what it says is a set of pairs of set of alignment information, okay? So what we're gonna do is we will introduce this variable A, which captures the alignment, and then sum of the alignment to make it a proper probability distribution, and then decompose it in this fashion, okay? Now, here we have to make a conditional independence assumption in order to write this part as a product of the alignment probabilities. So first of all, like what the alignment variable or the table looks like, what you'll see is that consider like you have an alignment table like this, where each row contains a pair of alignment information. So usually it's given by index, right? So the first, it's basically some French word, sentence, or whatever the granularity is. You have the French indexes, and then you have the corresponding English or target language indices. So you have, we use such kind of alignment variable in order to decompose this. And the assumption that we make here is essentially, and together this row is actually called a bead. The assumption that we need in order to decompose into this equation is that none of the beads, none of the words, let's go with words, none of the words in a bead flows into any other bead. So if I say that a bead or a word or a sentence belongs to a certain AI or index I, then they are conditionally independent from any other indexes. So so does that make sense? So any word or sentence appearing in one bead, they do not appear in any outside of that bead. They don't appear in any other index. So that makes them conditionally independent. So with that assumption allows us to just like, have a product of probability of FAI and EAI of that alignment, okay? So we can, does that make sense? Okay. Sorry? Yeah. Oh, the decomposition. But okay, so let's. I think that's a better example in a couple of slides. We'll come back to that question. Yeah. So from our knowledge of typology, we know that the words and phrases can be out of order. So when you do your assignment, you're already given the Hansard corpus where someone has done the alignment for you. But someone had to. There has to be a process to do this alignment in the first place, even if you're using neural models. Because think of the training batches. Who gives you that batches? You have a very nicely aligned batch of like French and English, whatever, and then you're doing it. But someone had to do the alignment. Yeah. So in practice, like we're not given. We don't start off with an alignment. We have to do this. So here we're going back to the question was that how does it actually like let's say we'll focus on sentence alignment first. And if you think about it, like sentence alignment, sentence is a good granularity for doing this, because if I give you a French document and an English document saying that these two documents are same, then you can sort of say that, okay, so then you can say that, oh, this paragraph and this paragraph, they're the same. And then within the paragraph, we have to do some kind of sentence alignment. And there we can see, so for example, in this here, we can say that this is a paragraph of, actually there's a dot, whatever, 7 sentences, and we're sort of trying to find the alignment. And this is what I mean by bead is, so what we're saying is that F1 aligned with E1 and E2. So with this example, he was happy, he had bacon, translates into something French, which I'm not going to pronounce, not to butcher it. But the idea is that you can have 2 sentences aligned to this one F1 sentences, and then we draw a line. And here, you see the conditional independence I was saying is that what if we had something like, okay, so then the next bead is F1 and F2 aligns to E3 and E4, okay? If we had this kind of alignment violating the conditional independence, then we couldn't have done that product probability. So that's what it's called the correspondence problem, or essentially that's the assumption that we make is that once you see a sentence, either source or target in one bead, it's done. You're not going to see that reappear in anywhere else in the alignment that you have chosen, okay? And so going back to your question, so does this sort of answer your question, or? Mm-hmm. It's like a word that doesn't exist in English, right? So it's so it's a sentence, right? Sentence level alignment. So we're saying that sentence E1, he was happy, and yeah, and he had bacon. E1 and E2 is aligning to the entire sentence. Okay? Yeah.
What does it mean for a sentence to be conditionally independent?
Sorry?
What does it mean for a sentence to be conditionally independent?
Okay, so the question was about the conditional independence. Okay, so what I mean is that here he was happy is E1, right? So we are defining E1 in our bead A1 here, okay? Right? So once we have sort of included in our alignment model, we are not going to see. So if you look at the yellow box over there, then F1, the first index is the French sentence. So F1 corresponds to E1 and E2. F2 corresponds to E3. So by conditional independence, what I mean is that this 1 and 1, 2 will never appear in any of this following beads. Okay? So basically, he had bacon will not map to any other French sentence. Okay, that's clear. Okay. Any questions? Okay. So yeah, as I said, that we need to first align the sentences before moving forward, and our goal is to find the best alignment that essentially gives us the best probability of the joint probability of F and E. How do we do this? We'll look at high level briefly on two broad classes of methods. One is based on the sentence length, and the second one based on lexical matches or cognates. As I mentioned, that most machine translation, including neural, relies on sentence level alignments of bitexts. So the first one is sentence alignment by length, which was introduced by the work of Gale and Charch in 1993. The idea is that it does exactly what it says. The idea is that, you know, short sentences align with short sentences, long sentences align with long sentences, and then there is a constant. There is a constant among different languages that we sort of know from our let's say from our experience that you know, what is the like English sentence of size X is usually a French sentence of size Y, something like that. So we have a constant C between the languages, right? So for example, like I think for French and English has a constant of 1.06, whereas German and English has something of 110. So idea is that if we know this, we have this constant that we know, and we're gonna create a cost function or penalty function based on this knowledge. This can be learned or guessed. You can look at like two different corpuses of English and English, like, oh, okay, yes, so French is a little bit shorter than English or something like that. And then we're going to say that the cost function could be something like that. The more you deviate from this known knowledge, I'm going to penalize you more. So let's say we know that English sentence is 1.5 times longer than a French sentence, and there's something that deviates like 2 times longer, then I'm like, okay, so you're going to have more penalty. So that's sort of the idea. And you define a prior fixed cost CIG of aligning I English sentences to J French sentences. Okay, so for example, in the previous alignment example, we had a bead that was that had 2 English sentences and 1 French sentence, right? So we'll say that Cij would in that case be like 2, 1. Okay. So we define a fixed prior cost, and based on this cost function and this prior fixed cost, we can have. Sorry. Now I've switched to the main view again. We can define a cost where the cost is the sum of alignment of all the beats. Okay, and this setup is essentially a canonical dynamic programming problem. You can solve this using dynamic programming. And using dynamic programming, you can find the distribution of sentence breaks or alignment that gives the lowest cost. And that's how we can get the alignments. And this in practice is surprisingly, has been surprisingly effective because even in like OCR cases where you have like the optical character recognition of 2 different languages, and you don't need any semantic meaning or anything. You just like length suffice to be a sufficient metric to sort of have a rough, very good alignment just using length. Given that we have those prior knowledge that, you know, the value of C and things like that, which can also be learned. Okay, so the second technique is sentence alignment by cognates. By cognates, what I mean is words that have a common etymological origin. What is etymological is pertaining to the historical derivation of a word, like pork is derived from the word pork, I think from Anglo-Saxon, or another example is the modern day word cartridge. Printer cartridge is derived from actually the Egyptian cartouche. Anyway, so the thing is that if words across different languages have, you know, common etymological origin, we can see some more examples over here, like zombie, zombie, government, government, then they will have some similarity in their spellings as well, okay? And which is not always true, but most of the cases it holds. thus, if we do that assumption, then we can use cognates as our anchors between related languages. And it doesn't have to be just cognates. If you think about proper nouns, right? So whatever your name is, like Andrew is going to be, Andrew did something and Andrew did something in French. The word Andrew is going to, the proper names are going to be the same, right? So they can also act as anchors. So the idea is that we use some kind of anchor in two languages, and then we try to do the sentence alignment. The way we do this is what Church in 1993, what he proposed was tracking all 4 graphs, which is 4 graphs are similar to 4-gram or n-graph. N-graph is essentially the same as n-grams, but for characters instead of words. So if 2 words have similar, like 4 characters, if they share the same 4 characters, then it would be considered as a cognate, okay? Or, yeah. So with that kind of setup, we can then we can draw up what is called a dot plot or a bitext map in some literature. And the idea is that you can concatenate the source and target side by side and top and bottom, and then you basically traverse the x-axis and the y-axis, starting from 0, 0 at the very top. And then you can place a dot whenever there is like, you see a cognate, okay? And yeah, so for example, like in this case, you can, let's say you're traversing and here at position I, some French word I, you can basically say that, oh, okay, here, there's a cognate over here. So same idea. So we're interested in the bottom left block and the top right block, because that's the mapping between 2 different languages. And if you draw up a diagonal like this, that sort of, then you can say that sentences along or near the diagonals is basically aligned with each other. And you can think about it that if you can, so if you can translate this information into this alignment table that we talked about, right? So over here, let's say you're like looking at this and you're saying that, oh, the P French sentence is aligned to the, like, I don't know, maybe there's like a sentence break over here. So this is the Q English sentence, and let's say this is within some French sentence. So what you're saying is that, okay, so I'm going to add an entry to my alignment saying that one of the rows in the beads is FP is aligned with EQ, and then move on and then keep traversing. So you get the idea, right? So you can sort of draw up an alignment table like that. And we already know from like how to work with, we've already defined this decomposition where we decomposed our translation model in terms of this alignment variable. And this alignment can be pairs of sets of like it can be of different granularities. It can be words, it can be sentences, it can be documents. If F and E are sentences, then AI are pairs of sets of sentences. So you get the idea. So, okay, so let's look at word alignment models. So how do we align the words? Okay. So if the granularity is word level, then we make a simplifying assumption. We make a simplifying assumption that the source, every source word So simplifying assumption is that every word in F or every word in source language maps to one target language, okay? So in this table at the bottom, we're using, this is really not French, this is Spanish, but let's say this is the foreign language, okay? So if we look at it, that every source language has a corresponding English word, okay? And it's not vice versa. Now, why do we need that? So basically what that allows us to do, again, think of in terms of that alignment table that you have. And then that allows us to sort of order the beads in a conditionally independent way. So we can always say that if I maps to some English word, okay, EJ. And this allows us to decompose this probability using what we have seen before as a product of F given E, okay? Now going back to this one again. And how can we get this guy, the probability of F given some English alignment? So that can be just maximum likelihood probability, right? So you look at the corpus, you count the number of times F has appeared, this word F has been aligned with this English word E, and then you divide it by the number of times that English word appears in the corpus. So it's just an MLE approximation, okay? But obviously there are certain problems with our word alignments. I mean, as we have seen that, you know, there could be some words that are not aligned with anything, zero mapping, or there's also a problem with order, right? So here Mary did not slap the Greenwich. The Greenwich part is, you know, the order in Spanish or the foreign language is not the same. So just word alignment models does not care about word orderings at all. So in order to circumvent some of the shortcomings of word alignment models, phrase-based alignment was introduced, and phrase-based translation was the most common form of you know, translation methodology before neural machine translation sort of took over. So the ideation with phrase-based translation is okay. So if you look at this, so think of now it's phrases. So each French and English, the beat contains non-contiguous empty spans of words. So now these are all spans of words instead of sentence order. These are spans. Okay. So think of this as like, you know, this English French span of French words, and that's mapping to English. And L can be this LU, okay? And what this probability decomposition is this, that basically we have the same thing as before. This phi is a joint probability approximation of French phrase and English phrases, okay? So this phi over here, this is something that we saw before. It doesn't really change. You just look at the corpus, you look at the number of times this French phrase and English phrases occur together, divided by you know, all the times they appear in the corpus, and you sort of approximate it. The new thing here is a distortion penalty. And the distortion penalty, think of it as, the intuition is that what is the overlap, or what's the distance between a corresponding French span? So I think it's easy to see it like this. Sorry. So when two okay, so let's say we have an alignment of two blocks of French phrases. If they're just side by side, then there's a minimum penalty. If they diverge, if the distance between them increases, then the penalty sort of increases. So that's sort of high-level intuition of this distortion penalty. You can read more about it in the text, but it's basically, think of it as you know, how much does it deviate, or how much the phrases are apart based on that kind of penalty. So yeah, so that's sort of like a high-level phrase-based translation methodology. And there's also another trick for calculating this phi function. So we just said that in order to calculate phi, we'll just count the pair of times, number of times this French and English pairs occur together. But there's a condition there. So we only count the phrases if it is consistent. So what is this condition of consistency condition? So the consistency condition has two criteria. at least one, there has to be one word in their partition, and those words that are there in their partition, they should not occur outside that partition, or they should not be contaminated by some other words. So it's best elucidated by this example, okay? So let's say you take Mary no, Mary did not. So these are the two phrases we're considering. And if you take their partition, and if you look at the first one is that there should be at least one AI. So there should be at least one corresponding word in there, and there's three, and it's all in the intersecting partition. There is no other contaminating words in their spans. So it's a valid pair, we'll count this. Let's take another one that violates it. So let's take the phrase the Greenwich and La Bourgeois Verde. If we do that, then the first criteria is satisfied, but the second criteria is not satisfied because there's this word A that is which is not in the span intersection, that is occurring in the span or the intersection partition, so it's not a valid, it's not consistent. And one thing to notice is that La Bourgeois Verde is actually a right translation of the Greenwich. So this just highlights that this is not perfect, then I mean, these rules are not perfect, there's always some inaccuracies. So yeah, so that's the idea, and I think that's all about phrase-based translation we're going to talk about. And then we go back to the missing piece or the remaining piece that we talked about at the beginning of the noisy channel formulation. So we know about language models. We learned about this F given E, the translation model. And now we have to do the decoding part. So observe some French and then decode that back into English based on our earlier formulation. But this is infeasible computationally because the number of possible, all the English words, the number of possible alignments or the number of possible EA joint probability is usually very large. So we do a heuristic beam search, and the high level idea is that we choose some partial translation with highest score, and basically we append that list, we prune anything that goes in the top K table, and then we continue like that. But this will cover that in the neural machine translation decoding part. And yeah, so I think we'll finish here exactly. We'll start with neural machine translation next lecture. Okay, thank you.